Is my screen visible?
Yes, sir, visible.
Right. Okay, so we'll start today's session. So this session again, it will be mostly on theoretical aspects of different kinds of world microstructures we observe, uh, like uh, like what happened in fusion zone, what happened in heat affected zone, what happened in like what happened during recrystallization and grain growth, and then we'll also discuss like what will be the phase formations, or in terms of product phase formation products in your iron carbon phase diagrams. Anyhow, you're familiar with those things, and we'll try to again brush up the things, recapitulate whatever you have gone through your video lectures, right? So we'll start today's session. Now, in fusion welding, if you see what is the heat affected zone, so if you see, the heat affected zone is, it is a area of a base material, either a metal or a thermoplastic, whatever you are doing welding with, uh, which is not melted but has had its microstructure and properties altered by welding, or these are some heat sensitive regions, right? So the heat from this welding process and subsequent recooling can cause this change from this weld interface to the maybe termination of this sensitizing temperature in the base metal. And then the extent of magnitude and property change, those mostly depends on this, what is the property of your base material. Like, there can be temperature dependent conductivity, there can be temperature dependent specific heat, there can be temperature dependent density. So all these material properties of your base material, or if you're using any kind of weld filler metal, that may be similar of base metal or also dissimilar, depending on your application. Those things basically affect your heat property during the welding, right? So here the thermal diffusivity basically of the base material plays a big role here. If the diffusivity is very high, what will happen? Like, the material cooling rate will also be high, and the heat affected zone will be relatively small, right? So if we talk about diffusivity, let's say copper or aluminum, if it is very high, what will happen in terms of uh, the width of the heat affected zone? So width of the heat affected zone will reduce compared to the less diffusive materials like maybe SS, right? So a low diffusivity leads to slower cooling rate of and larger heat affected zone. So here it will be larger cooling rate also, and vice versa for less diffusive material, right? Now, yeah, the amount of heat input during this welding process also plays a role, in in oxy-fuel welding, it use high heat input and increase the size of heat affected zone. Again, for process like laser beam welding or electron beam welding, those are kind of very much concentrated, right? So there will be limited amount of heat resulting in a small heat affected zone. So those things matters. How can we calculate that, how much heat is getting into the welding zone? So if, let's say, if you have Q, which is your heat input in terms of kilojoule per mm, and then let's say for your arc welding, you have your voltage, you have your current, and you have your you have your, this is your welding speed. Okay, and then you'll have to have some efficiency, which is depending on the welding process, right? Now, here what will happen? So heat input per unit length, I have already discussed it. What will be the heat input per unit length? Anyone? Right now. So it depends on how speed, in which speed you are doing welding. Depending on your welding speed, also your cooling rate and those things will vary, and finally it will affect your weld microstructure. Correct. And then if you try to draw some figure, if you try to draw some figure that how this weld microstructure looks like in distinct zones of welding. So let me draw some figure. So let's say this is my weld bed. Okay, this is my welding bed, and here you will have some columnar kind of dendritic structure. So what is this region? What is this region? Anyone? What is this region where this columnar kind of structure you will find out? This is basically your fusion zone, right? Where your melting has been taken place, and after melting, there is your solidification, and then some boundary will be there where. Am I audible? Hello.
Yes, sir.
Okay, great. So some boundary will be there, which will be your fusion line, right? And then there will be some fine grain heat affected zone, then some uh, so depending on your cooling rate, there will be distinct zones in your heat affected zone, right? So the actual cooling rate with which the weld cools, the composition of base metal, and the whatever flux you are using, those things decide the overall microstructure of weld during, maybe in terms of, if you are thinking of this iron carbon, so the during transformation of austenite to ferrite, right? So whenever the weld has been cooled, it is poly-staged, and then observe. There will be three distinct metallurgical zones, as I was saying. Like there can be weld metal zone or fusion zone, fusion zone. There will be heat affected zone, and finally there will be unaffected base metal, right? So the region which lies between the weld and the base metal, that is called the heat affected zone. Correct, no? Now, as I was saying here also, the microstructure of this heat affected zone depends on the peak temperature reached. What is the peak temperature, right? And also the time. So you are providing sufficient amount of time to diffusion to happen in that temperature range, right? So depending on that also, your microstructure will vary. So in heat affected, sorry, in heat affected zones, what are the different regions? There can be some coarse grained heat affected zone. There can be some coarse grained heat affected zone. Then there can be some fine grained heat affected zone. Then there can be some maybe intercritical or subcritical heat affected zone, right? So why coarse grain heat affected zone appears? What are the main mechanism? So coarse grain heat affected zone may happen due to slow cooling. So slow cooling causes this base metal to undergo, uh, what is annealing. So basically, because of slow cooling, annealing is happening, which results in this recrystallization of base metal by forming some fresh grains, and then those grain size becomes little bit larger than the original size, but it is smaller than the grains of welding. So these are your columnar grains, right? Then you will have some coarse grain heat affected zone over here. So because of some temperature gradient, a little bit of grain growth also will happen, and this is your coarse grain heat affected zone. And then beside that you will have fine grain, correct? And then finally you will have some unaffected base metal. Now we have already discussed in terms of grain growth what is, like, you have this epitaxial growth, different kinds of growth mechanisms we have already discussed. And then we have also discussed, uh, what will be the conditions for these different kinds of solid liquid interface, right? So in terms of solid liquid interface, depending on your G by R ratio, so temperature gradient and growth rate ratio, you'll have some planar solid liquid interface, you can have some cellular interface, you can have some uh, dendritic structure. Those things we have already discussed. So any question from here? So okay, so coming to the question, the heat effector zone associated with a weld is, what will be the right answer? Can anyone respond?
Second option.
Second option, correct. So this is the area immediately adjacent to the weld which has undergone a microstructural change. Right. So if you see this final weld metal grain structure, it has considerable practical significance, right? So it has been shown that a coarse columnar structure is susceptible to hot cracking, whereas a finer grain structure, a distorted columnar structure, or an equiax structure is more resistant to hot cracking, right? In addition, if you see the fusion zone grain structure, this has strong influence on these mechanical properties also. So to improve this mechanical behavior and hot cracking resistance, weld metal, there have been a lot of efforts to understand the weld microstructure and to find out different approaches. If we can somehow, like, there are some approaches of alloying also which can make the refined grain structure. So as I have already discussed, refined grain structure is, like, for defined grain structure, this is very much suitable for higher weld strength, right? So any question from here? Whatever discussion we have done in terms of theoretical, of course.
Sir, in the assignment, we had the
Mhm.
same question, but the answer was given, it was the third option.
The oiled area plus the parent plate, which has undergone a microstructural change.
Parent metal will come in HZ, right?
So no, here it says that the
No, I
parent
mean,
plate, which has
weld,
undergone a microstructural
yeah.
change, but in terms of like this is adjacent to the actual weld metal zone or fusion zone. The heat affected zone is not within this weld metal zone, right? So
Yes.
weld metal zone is having this columnar kind of structure because of higher temperature gradient and highest cooling rate, because this region is coming into the peak temperature. uh, so if you ask me, according to me, this should be the correct one. I'm not
The
aware
weld
of
area
this.
doesn't come. Weld area doesn't come under HA.
Come again. Weld area doesn't come under HAZ.
Heat affected zone. Yes.
Yeah, that's what I was telling. That's what I'm telling. That this is a separate part, and heat affected zone is adjacent to that. So here your melting and solidification both are happening, and because of that you are having that kind of microstructure. Because right, but in heat affected zone there should not be any kind of melting, but uh, because of some effect of temperature and those things, you are having those recrystallization and grain growth mechanisms happening, and without being melting, the microstructural changes are happening, and whatever mechanical properties are there.
Yes.
Maybe you can clear your confusion with professor. That will be much better if it is having some different answer it is providing.
Okay.
You'll have some separate session with him, right?
I don't know.
I'm not sure anyhow. ठीक है. The concept is I hope clear.
Yes, sir.
Great. Okay. So as I was saying that in heat affected zone there will be different kinds of microstructure, and there are two different mechanisms here. One is this recrystallization, and then you have something called grain growth. So before recrystallization, again there is something called recovery is also there. So if you see, metals can be strengthened in several ways. It can include some kind of solution hardening. It can include some kind of work hardening. It can include um, what should I say, precipitation hardening or transformation hardening. Different mechanisms actually happen during this weld microstructural change, and the effectiveness of these methods can be reduced significantly by heating during the weld in the area called heat affected zone, right? Now what happens during recrystallization? So how should I explain? Like, you are aware of this forming process, right? When a metal is cold worked and plastically deformed, for instance cold rolled or extruded, right, what will happen? Numerous amount of dislocation will be generated, right? And this dislocation can interact with each other and form dislocation tangles, correct? And these such kind of dislocation tangles hinder the movement of newly generated dislocation, right? So in forming process, in this way, a metal is strengthened or hardened by cold working. What is this mechanism called? What I told just now is called work hardening, right? Now, most of the energy expended in work hardening appears in the form of heat. है ना? So, if you try to figure out a graph, if you try to figure out a graph, so let's say this is my percent elongation. This is my stored energy, and this is my fraction of energy stored. Okay, so this is my energy. So what this is showing, this is telling that a finite fraction is stored in the material as strain energy. Okay, so whenever a work hardened material is annealed, the deformed grains in the material tend to recrystallize by forming fresh and strain free grains that are soft, just like grains that have not been deformed, right? And the stored strain energy is the driving force for this recrystallization of this work hardened material. So you are having some stored strain in, sorry, stored strain energy is the driving force. Now, what do you think? With increase in annealing temperature, the extent of recrystallization will increase or decrease? It must increase. The extent of recrystallization always increases with increase in annealing temperature, right? And it can be expected that the strength or hardness of a work hardened material tends to decrease with increase in annealing temperature and time. So again, if we try to draw some graph over here, so with annealing temperature, and let's say this is my strength, it follows some curve like this. Okay, so in fact, before recrystallization takes place, there exists a period of time during which certain properties of work hardened material, for instance, let's say electrical resistivity, tend to recover without causing any microstructural change, and this phenomena is called recovery. I was saying that, so before recrystallization you will have something called recovery. It is trying to recover from its strained region to a strain free region, correct? And however, since this mechanical properties of this material, such as strength or hardness, those do not change significantly during recovery. Those changes happen during the recrystallization happen, right? And then what about grain growth? So grain growth happens upon completion of this recrystallization. So upon recrystallization, whenever it is completed, grains begin to grow. What is the driving force for grain growth? The driving force is the surface energy. So the total grain boundary area and the total surface energy of the system can be reduced if fewer or coarser grains are present. So you are getting my point, right? So if you have some few grains, like if you have a few grains like this, or coarse grains, let's say this is my coarse grains, and here you have some fine grains over here, right? Which one will have which one will have the higher grain boundary area? This one, right? So if fewer and coarser
Yes,
grain
sir.
are present, the total grain boundary area and thus the total surface energy of the system will be reduced. Here, the surface energy will be reduced, right? So, like recrystallization happen, the extent of grain growth also increases with increase in annealing temperature. So here I'm not drawing anything. So this is common sense, right? So if initially you are having some smaller grains, then because of some heating it up, you are having some fresh grains produced, which are initially it was and which are undeformed strained free grains, and with time it will start to grow, which is called the grain growth, right? And hmm, hmm. So in terms of effect of welding parameters and process, so in terms of effect of welding parameters, both the size of heat affected zone and the retention time. There is some question that what is retention time. I'm coming into that. So both the size of the heat affected zone and the retention time above the effective recrystallization temperature. So those increases with increase in heat input per unit length of the weld, right? So if you are having heat input per unit length, this increases size of heat affected zone and retention time, those increases. And as I was saying that heat input per unit length is q by v. So depending on welding speed also, your cooling rate also vary, and which can vary your microstructure. Let us graphically represent the thing. Let us graphically represent the thing. So let's say this is my fusion zone and this is my heat affected zone, and then this is my fusion zone and this is my heat affected zone, and then this is my fusion zone and this is my heat affected zone. So what is happening here? So you are basically increasing the heat input per unit length of the weld. Heat input per unit length of weld is getting increased in this direction, and you are getting wider and wider fusion and heat affected zone, correct? And then let's say this is my point 1, this is my point 2, this is my point 3. I'm comparing the strength and hardness. So if we do some graphical representation, this is my distance from, so this is basically distance from the weld center line, okay? And here you have the strength property. So the one will have this amount strength, the two will have this amount of strength, the three will have this kind of strength. This is my for point 1, this is point 2, and this is point 3. Okay. Any question? So coming to the question, can we figure out which one will be the correct answer? So it says that toughness of heat affected zone is affected by chemical composition, microstructure, and grain size. This is true, of course. And it also says that aging grain coarsening in underbit zone leads to degeneration of plasticity in underbit zone. This is also true, right?
Yes.
But is this the correct explanation for statement one?
No, I don't think.
Right. Statement two is not the correct explanation. Hmm. Should I move to next question then?
Yes, sir.
Okay. Which of the statement are correct about heat affected zone? Okay. This is regarding some polymorphic transformation. Can you tell me what is polymorphic transformation? What happened during polymorphic transformation? Any guess?
Same element can exist in different, like, yeah, can have
Correct,
different
correct, correct.
physical structures.
So polymorphism is basically the ability of a solid material to exist in more than one crystallographic form or structure, right? So this is one of the secrets to the success of iron to combine with other elements and to form some alloys such as steel, what we use, and it dramatically extend its range as an engineering material. So at room temperature, the most stable form of iron is which one? This is BCC structure, body center, known as ferrite or alpha ferrite, right? And in this state, iron is relatively soft and can dissolve only a small amount of current, not current, sorry, small amount of carbon. So in room temperature, small amount of carbon can be dissolved at soft state, right? And what will happen above some upper critical temperature? I hope the upper critical temperature is somewhere around 900 degrees C. So what will happen above the upper critical temperature? So those alpha ferrite undergoes a phase transition from this BCC to FCC structure. It's called gamma austenite, right? And austenite is also relatively soft, but can dissolve considerably more amount of carbon, as much as some 2% of carbon at uh, some 1100 degrees C. I don't exactly remember anyhow. And finally, above 1400 degrees C, what will happen? The upper one, and up until the melting point of iron, what will happen? This austenite, what transformation will happen? So this FCC structure will be back to BCC structure, is it not? So the most
Yes.
important that is del what was it? delta ferrite. So you have this delta ferrite, then you have this gamma austenite, and then you have this alpha ferrite. Correct, no? So
Yes.
here it says which of the statement is correct regarding heat affected zone. Microstructural change in heat affected zone remain unaltered for metals or alloys without polymorphic transformation, with polymorphic transformation, and or it says polymorphic transformation has no effect. This is not true, of course. This is also not true. Statement 2 is correct. Am I right?
Yes, sir.
So coming to this, so basically the retention time, what is retention time? It is basically the peak temperature, the time at which the peak temperature is maintained during the welding, that is called the retention time. Okay. Okay. So now coming to some concepts regarding this stress corrosion cracking. What happened during stress corrosion cracking? Before that, can you tell me what is the correct one? So here it says that it leads to growth of crack formation in a corrosive environment. Of course, this is true. Leads to unexpected and this is also true. And the presence of some chemical compounds like sulfur, it can be chloride or some alkalized element. The reason for stress corrosion cracking. This is also true. So what will happen? What is stress corrosion cracking? So if we try to define this, uh, let me define in this way. Like stress corrosion cracking is kind of propagation of often branched cracks. So if you have some crack in branch like this, let's say, and it has initiated and then it is getting propagated, like what happened in brittle failure, right? Within a corrosive environment, potentially leading to a catastrophic failure, and then so basically it appears like a brittle failure because of that crack propagation mechanism. So this form of corrosion can occur as either something called intergranular stress corrosion or something called transgranular stress corrosion. What is intergranular stress corrosion? So here the fracture forms along the grain boundaries of material, and if you have transgranular, it fracture happens through the grain of material. So this is not along the boundary. Okay. Now, what causes stress corrosion cracking? There are basically three main factors that work in combination to affect and cause this stress corrosion cracking. So there can be some effect of material, there can be effect of environment, and what else? There can be some effect of maybe residual stress, some internal stress generated during welding, right? So in terms of material, like different kinds of material are more or less susceptible to stress corrosion cracking, right? So poor material selection can lead to this kind of cracking due to material being susceptible to it in the corrosion environment. And what environment I'm talking about? So as I was saying that there can be some chemical species which causes this kind of corrosion cracking, and as a result material and environment selection, those are very much important, right? And yeah, in terms of residual stress also, this involves this material experiencing this stress or strain from either this residual stress or maybe some direct application of stress or pressure depending on your application, right? Now how can we prevent this stress corrosion cracking? So in terms of material, simply you have to use some material which are non susceptible, right? So yeah, and also in terms of environment, you can remove or limit or replace the relevant corrosive chemical species what you are trying to, and this can also prevent this corrosion cracking. And however, this can be very difficult factor to control if corrosive species are naturally present in environment. So most of the time there will be corrosive agent in the environment. So in terms of in controlling the environment, this is very much difficult, right? Any question?
Yes.
Okay, I think this age hardening process we have sometime initially have discussed anyhow. uh, can you tell me an example of, so age hardening is basically a kind of precipitation hardening which we'll discuss in the which we'll discuss in the subsequent discussions. So can you tell me any kind of alloy which is an great example of precipitation hardened materials? What I can think of, there can be some aluminum copper alloy. So here, if you see in aluminum copper alloy, just give me some time. I was searching for this aluminum copper phase diagram. So what I can see here for aluminum copper phase diagram. So let's say this is my weight percentage of copper, and Here is the temperature. I'm just drawing the left hub portion. So the eutectic region basically. So here this is my liquid, and this is my alpha aluminium, and this is your theta. So some phase formation is there of something called Al2Cu phase and aluminium. Okay. Now here the solubility of copper in this alpha phase increases with increase in temperature. This is a necessary criteria for precipitation handling. So what I was saying that solubility of copper in alpha phase increases with temperature increase, right? Now, what are the different steps involved during precipitation hardening? So there will be some solution heat treating, that is to heat treat the alloy in the alpha phase temperature range until it becomes a solid solution. Then you do quenching, right? So basically rapidly cool the solid solution to room temperature to make it super saturated in copper, let's say. And then you do aging. Aging is to allow this strengthening phase to precipitate form and the super saturated, you make some super saturated solution, correct? So the steps what I am talking about, you first you heat it up and then quench it and then you do aging, right? Now aging by heating is called artificial aging, and aging without heating is called natural aging, correct? Now then we discussed some Gunnar Pritson Jones, right? So do you remember what happened during that time? So if you are doing some artificial aging, let's say we are doing some, let us recall the thing. I'm also trying to recall the thing. Uh, let's say you are doing some artificial aging of aluminium copper alloy. Okay. So what are the structures you can form during artificial aging? So initially you will have super saturated solution, as I was saying, super saturated solid solution, and then you have this GP region. From there you have this precipitate formation. I'm coming to those things, and then finally you have this theta L to Cu. What is theta L to Cu? This is the equilibrium phase. So theta L to Cu is some equilibrium phase, and this GP zone, and then you have this theta double dash phase, sometimes called GP2, and this theta dash phase. These are metastable in nature. Now if we try to find out what will be the hardness property or strain property of different regions with aging time, uh, this we had figured out. This we had figured out during our earlier discussions. Anyhow, I'm trying to recall the thing again. What will happen for an aluminium copper during as an effect of aging time? So this may look like something like this. So if this is your aging time, let's say my x-axis is aging time, and let's say my y-axis is Vickers micro hardness. So I'm measuring it. I'm measuring the Vickers micro hardness. Okay, and this will be something like this. So here you'll have this theta precipitates formation, and here this is my GP region, and here somewhere here there will be theta double dot precipitates, and you finally form this theta L2Cu. Do you remember this? So basically this shows the correlation of this structure with the hardness of aluminum copper, right? So when the maximum hardness occurs when the amount of this theta double dot or the GP2 region is at a maximum, right? Although the some contribution may also be provided by this theta dash precipitates. So whenever this theta dash precipitates grow in size and increase the amount, what does it called? This is called overaged solution. Okay, and as aging continues even further, this theta phase starts to form, and the alloy is softened far beyond its maximum strength condition. So here your maximum strength is there, but this is metastable in nature, and with aging time you form this L2Cu precipitates, which the strength of which is much less than what is there for this theta double dot or theta dot precipitates. Okay. Any question from here? I was trying to brush up again the thing. What I think we discussed this aging treatment earlier. Yes or no? Anyone there? Guys, am I audible?
Yes, sir, I couldn't understand. Like, what is it?
Okay. Okay. Any question up to this?
No, sir.
Otherwise, we'll move to the next one. Okay. Okay, so coming to the next question, this is some concept regarding strain age embrittlement. What happened during strain age embrittlement? So if you try to define the strain age embrittlement, this is kind of change in the properties of a cold work metal over time. So this is kind of change in the properties of cold work metal, or we can say steel for the present purpose, cold work steel over time. So whatever changes you observe, whatever changes you understand in terms of microstructure, this occurs rapidly at higher temperature and only in steel that has been cold work. So for strain aging to occur, two components are necessary. You can say the first component is stresses must be induced into the steel prior to the process, and this normally occurs through cold working, right? So you apply some deformation based process and you induced some internal stress into the structure. So cold working, what are some cold working process? uh, can you give me some examples? What what are some cold working process you have come across? Any kind of forming operation?
Rolling.
Rolling. Rolling? Anything else? You can simply do some punching operation. That is also a cold working. You can do some bending operation, or maybe some shearing operation. Yes, as you said, rolling. So stretching is also there. Correct. So if the stresses from these cold working practices are not relieved, they become points of high residual stress, right? During the process and can lead to strain edge embrittlement. So the first component is to strain edge embrittlement to happen, induce some residual stress which are which cannot be relieved. What is the second component? Like what is another option of reason for which strain edging can occur? Sometimes there can be impurities also in the steel, right? Such as those found in some lower quality steel, say used for reinforcing bars. So if you see, if a part cracks due to strain edge embrittlement, the cracking occurs immediately, but is also often seen at the job site as in the case of reinforcing bar. So it happens immediately after some application of load. So some simple amount of handling, or just after some repetitive use, it just happens that this embrittlement happens due to those impurities in the steel, or this induction of residual stress. So there are several ways to reduce this occurrence of this strain age embrittlement, but all methods focus on one aspect: reducing the stresses induced in the steel. So instead of cold working, which induce stress into the steel can be hot worked also, right? At some higher temperature, depending on your application, of course. So if it is necessary to cold work the steel, relieving the stresses induced from cold working can be accomplished by heating the steel for uh, maybe somewhere around let's say 1200 degree Fahrenheit to 1300 degree Fahrenheit. I'm not sure. So you can do that hot working. So you're basically annealing the thing, right? So there are other ways also. Let's say you are bending the steel. It is best to allow for a bend diameter at least three times the section thickness. So if you're bending the thing, bend dia can be three times the thickness. So this you can say as a design parameter to relieve the internal stress in between. And if you're doing some punching, when punching is necessary on this thicker steel, the holes should be reamed at least some 1/16 around the edge of the hole. Okay. So yeah, these are some approaches through which you can basically reduce the occurrence of strainage embrittlement. So coming to the question, it says that strainage embrittlement is process of change in atomic structure to produce a different from form process where steel becomes very brittle in areas of high stress when exposed to elevated temperature. Which one is correct? Huh? Which one do you think is correct for this strain age embrittlement? Maybe this is also a correct option. And this one. Do you agree? So two things are there. One is this residual stress, maybe, or your if your their internal stresses you can't relieve, that time strainage embrittlement will happen. And if there is some kind of impurity, or here it is telling that you are inducing some ductile to brittleness in the cold atmosphere. Whatever I was saying in terms of cold working, right? No, moving them. Already confusion is there.
No, sir.
Great. So moving to the next question. This is regarding some preheating of weld metal. Now, what is preheating? Is preheating in welding is kind of it uses to help ensure that weld quality and reduce the occurrence of cracking and other problems that can result, right, during welding. So it is commonly used before welding steel or steel alloy pipes or plates of different thicknesses. Why preheating is required, or what is preheating? So this process of preheating involves heating the area around the weld joint or the entire part to a specific temperature before you do complete welding, right? So preheating basically it reduces the cooling rate. It reduces the cooling rate of the weld and drives out moisture, which finally in terms helps to prevent hydrogen buildup or which are potential for cracking, right? There I think I have heard of this hydrogen embrittlement because of moisture entrapment during the welding. So if you are doing some preheating, those things also you can reduce. So several methods can be used for welding preheat, including some induction preheating or open flame preheating, or you can do some resistance heating. Uh, you can use some ovens also. Each one has benefits and drawbacks depending on their application, right? So the best preheating method for a specific application often depend on different parameters. You can have some material thickness, you can have size of the weld pool size, or uh, maybe some time of diffusion, and finally you have the cost also. So when to use welding preheat? As I was saying, that determining if a welding application it requires preheat, and it depends on several factors including the type and thickness of base material, right? So what are the different process I was telling regarding this preheating? There can be induction preheating. So what happens during induction preheating? It creates a magnetic field, right? It creates a magnetic field that generates some kind of eddy currents within the base metal and heating it internally from within, right? So it creates with magnetic field and that generates the eddy current. And then you have some open flame heating. So you can use some fuel gas plus compressed air like you do in gas welding, है ना? So you mix oxygen and acetylene and generate some flame, and depending on your ratio of this oxygen acetylene, there will be some neutral flame, oxidizing flame, carburizing flame, right? Then you can have some resistance heating also. The basic principle is like what happened in resistance spot welding. So this uses electrically heated ceramic pads basically placed on the base metal, and these heated tiles transfer the heat to the part through radiant heat or conductive heat. So it depends on electrical resistance of parent metal. Hmm. So coming to the question, what will be the correct one? So it says that it reduces the rate of heat loss from weld area. Yes, it reduces the heat loss from weld area. It reduces the moisture, grease, and oil from the surface also. And also it reduces the crack formation by preventing formation of hard surfaces. Questions? Any question?
No, sir.
Okay. So we have three more questions. This is a numeric one actually. So again, this is from lever rule, which you are familiar with. Can you please try to solve this one? So it says that for some 99.65 watt percent Fe and 0.35 watt percent carbon alloy at a temperature just below the eutectoid, we need to determine the followings. We need to determine the fraction of total ferrite and cementile phase. We need to find out the fraction of pro-eutectoid ferrite and pearlite phase, and then finally the fraction of eutectoid ferrite. So your C naught is 0.35 watt percent. And if you see this eutectoid part of this iron carbon, correct me if I am wrong, this is somewhere around zero point 0.7 point, this is zero point 0.7 and this is 0.02.
It's point 0.8.
That's point
Point 8.
eight. Yes, sir.
Point, point
Yes.
8. This is point 0.8. And this is your gamma austenite, and this is your alpha plus gamma, then this is your alpha ferrite, and then you have this alpha plus Fe3C. So this is my eutectoid temperature of how much? Some 720,
723.
723, 723. So okay, and then you have your C naught composition as 0.35, somewhere in between. Go ahead. What will be the weight percentage of alpha here for 0.35 weight percent? It says just below the eutectoid. So we'll take the final 6.7% of carbon, right?
6.67.
So 6.67, 6.67, 6.67 minus 0.35, that divided by 6.67 minus 0.02. Am I right? So this part is alpha and this part is Fe3C. How much is this coming?
95.04%.
95.04%. Great. And what about what percent of Fe3C? So this is somewhere 0.35, and then you have 0.02, and then we have 6.7 minus 0.02. Sorry, 6.67.
4.96.
How much?
4.96.
4.96%. Right? This was my first question. Coming to next question, what it asks about, it says we need to find out the fraction of pro-eutectoid ferrite and pearlite. So how can you find out the pro-eutectoid ferrite and pearlite one? Hmm? So if you want to find out pro-eutectoid ferrite and pearlite, you can basically use the lever rule or a tie line that extends only to the eutectoid temperature. Here, up to this, not below that, right now. So if you are using this one for perlite, how much it will be coming?
0.35 minus 0.02 divided
Divided
by
by zero point 0.8 minus 0.02.
0.8 minus 0.0.
And for your pro-eutectoid ferrite, which is, I'm denoting this as alpha, this will be zero point 0.8 minus 0.35, that divided by zero point 0.8 minus 0.02. Correct? Huh? How much are this coming?
Perlite is 42.31.
31%.
Sir, 32.31.
ठीक है. And pro-eutectoid one, 100 minus 32.
Perlite is 42. 42.
42. This would be somewhere around 58. Is it coming okay?
Yes.
Okay. Then you need to find out the fraction of eutectoid ferrite. So all ferrite is either as coming as pro-eutectoid or eutectoid, right, in the pearlite. So summation of these two ferrite fraction equals this fraction of total ferrite. So you have this alpha dash and you have this eutectoid alpha ferrite. And that is coming as final total ferrite fraction. So we have find out this is known for you, and this also you have find out that the fraction of total ferrite here, the W alpha one, right? How much was this coming? W alpha,
95.04.
okay, so this is something like 95.58, 57%. I'm not going through the detail of this again, of phase, iron carbon phase diagram. Anyone joined now? Any question from here?
No, sir.
Right. So coming to this post weld heat treatment. So if you see this post weld heat treatment, it generally refers to any kind of heat treatment performed after welding to improve the mechanical or chemical property of the surface or weldment what you were working with. So as I have said already that welding induces some residual stress in a structure, right? Which causes distortion also in the structure in the long term, correct? So this magnitude of stresses increases in more complex or bigger parts of structure. So during the welding process, when the metals are joined together, hardening occurs in different degrees based on this carbon content in metals, specifically in heat affected zone. So these are some points I have already discussed upon. So typically this post weld heat treatment is used to reduce this residual stress and enhance the resistance to brittle fracture. Additionally, uh, it can lead to some strength enhancement also and some hardness reduction, right? So this post weld heat treatment and stress relieving are the most commonly used procedures for this post weld heat treatments. Now what happens during post heating? What happens during post heating? So again, I have already told that it can decrease some potential hydrogen induced cracking, right? So hydrogen induced cracking typically occurs when the weld has some sensitive microstructure or high level of stress or sufficient level of hydrogen or moisture in the environment. So if you see in ferritic steels, hydrogen embrittlement occurs at temperature close to ambient temperature, and and cracking is very much susceptible there, right? So you have to do some post well heat treatment, like the heat treatment processes. So anyhow we have already discussed, like annealing, normalizing, tempering, depending on your application, what kind of microstructure you want in your uh, what kind of microstructure you want in your structural joint. And then there is something called stress relieving heat treatment is applied to to relax the stresses locked in the weld structure due to this welding process. And the residual stresses are relaxed simply by heating a structure uniformly to a sufficiently high temperature, and then you subject it to some thermal retardation for some specific duration based on your material thickness maybe, and then you're basically doing some uniform cooling over your structure, right? So however, during this stress relieving, what happens, you don't heat up above this upper critical temperature. You must remain under this lower transformation temperature range. For instance, for this carbon steel are heated somewhere around something around 600 to 675 for some specific hour. I don't know what is the hour. Anyhow, so thus this stress relief heat treatment reduces the risk of cracking in the weldments by reducing their hardness and increasing the ductility also. So I want to share some study published in some journal. Here the researchers investigated the effect of this post-weld heat treatment parameters, including this holding. There are two different parameters like holding time and holding temperature. These are the two parameters, effect of these two parameters on relaxation of welding residual stress in EBW. What is EBW?
Electron beam welding.
So they did some process parameter study of holding time and holding temperature on this relaxation of welding residual stress of some steel plates maybe, some steel plates during your electron beam welding. So here they basically developed coupled thermomechanical model, coupled thermomechanical model in the sense that you are having both mechanical stress are getting generated and also you are analyzing the temperature. So there will be some temperature dependent material properties you are using. Don't go into the depth anyhow. So they basically developed some thermomechanical model to simulate this electron beam welding process. And while this post weld heat treatment was implemented, right, and the holding temperature was kept constant at 770 degrees C, and holding time was varying to assess the effect of holding time on the residual stress relaxation. Holding time varied. This was one case. And then similarly, holding time was kept constant at 1.5 hour to determine the residual stress relaxation at different holding temperature. Let's say some 500, 600, 700. You know? So the findings demonstrated that holding time was significant for only up to 2 hours, and no considerable relaxation in the residual stress was observed after that duration. On the contrary, a higher relaxation in the residual stress was observed with the increase in holding temperature, right? What does it indicate? It was indicating that influence of holding temperature was significantly higher than the holding time. So during residual stress relaxation. Okay. Is there any disadvantage of post weld heat treatment? Yes, there can be some loss of strength, like if you do some excessive holding times or temperature for stress relieving. Post weld heat treatment can reduce the strength of the material. So there must have some optimization while you are choosing your holding time or holding temperature, right? So moreover, this tempering treatment can also reduce the strength and of the quenched and tempered materials, right? So as I was saying, there must be some optimization. Otherwise, there is some no use of practical application. Correct. Hmm. So this is the last question on your distortion. So it says that austenitic stainless steel have a high thermal expansion coefficient or low thermal conductivity. What do you expect? Will it have significant distortion? So if you see the are you guys there?
Yes, sir.
Good. Okay. So a few more time. So if you see distortion in welding, like there can be something called solidification shrinkage. So you are melting and then solidifying. So there can be, depending on your what should I say, this coefficient of thermal expansion. This was my thermal strain, correct? Thermal strain. So
Yes.
depending on your coefficient of thermal expansion, there can be some solidification shrinkage and thermal contraction of this weld metal. So always your workpiece will have some tendency to distort. So if you see different types of distortions, if you see different types of distortion, there can be like, let's say this was your initial shape of your parent metal. So there can be distortion like this. There can be distortion like this. So this is transverse in this direction. There can be distortion like this. This is longitudinal. Or else you can have some, let's say, angular distortion also like this. So initially it was all straight and then you can have some angular distortion, right? So yeah, if you see this angular distortion usually occurs when the weld is made from the top of the workpiece. No? So angular distortion and weld is made from top of the workpiece, and then the well tends to be wider at the top than at the bottom, causing more solidification, shrinkage, and thermal construction, no thermal contraction at the top of the well than from the bottom. So basically, you are having some difference in your thermal expansion. Because of that, some thermal strains are getting generated, and because of that, you are having some distortion, right? What can be the remedies to avoid this distortion? So there can be several techniques, like you can reduce the volume of the weld metal, which can reduce the amount of angular distortion or maybe lateral shrinkage. And then you can do some design optimization also, like if you do some double V joint or single V joint, those things can reduce your angular distortion, or somehow if you can reduce your temperature gradient, or if you can play with cooling rate, all those things will ultimately affect your weld microstructure, and finally will affect in your weld performance in terms of this whatever distortion you are um, seeing, है ना? So yes, for this question, if you are having a high thermal expansion coefficient, if you are having a high thermal expansion coefficient, which is alpha, and a low thermal conductivity, so heat cannot dissipate basically. The thermal strains what it will generate, this will be huge, right? Have you done any kind of lab experiment, right? Let's say this is your substrate, and here you are joining some plate like this to this. So here you are joining this, and here all the things are clamped properly. If you see, this plate will be distorted over the time because of temperature. Temperature in the sense because of thermal strains generated. Here you have fixed it, so lot of uh, residual stress or internal stress in terms of tensile or compressive whatever, it will be generated in between, right? And because of those traces, and also depending on your thermal expansion coefficient, thermal strains will be generated, which will ultimately distort the workpiece. Have you ever seen the distortion in your workpiece after welding? Hmm? Anyone awake?
No, sir, not.
Okay. Anyhow, any question from today's session?
No, sir.
Great. So we'll finish it here. Meet next week again. Okay.
Okay, sir. Thank you, sir.
Have a good night. Bye bye.
Hello.